Alright folks, let's do number 50 here. And I don't know why my pen is acting weird. That's kind of strange. I wish they would take these retarded features off. But anyway, that's a different story. Alright, let's do the video. Air is blown into a spherical balloon so that when its radius is 6.550 centimeters, its radius is increasing at a rate of 0.9 centimeters. Alright, so I encourage you guys to pause the video and to give this problem a shot. Before I answer part A, part B, or part C, I want to get this out of the way. Find the rate at which the volume of the balloon is increasing. I know, folks, I haven't attempted to solve these problems before I press the record button. It's just the way I roll sometimes. Maybe it's not a good idea, but it also has its benefits too. And the benefit is, you can also figure this out, especially if I can. All right, so we have an air balloon into a spherical balloon. So let's draw the balloon. You have a balloon. That's a crappy balloon. Maybe I should use that feature. Let's try one more. Let's try one more. Good enough. Anyway, so you have a balloon, a spherical balloon, and its radius, and it has some radius. The volume of that balloon is going to be 4/3 pi r cubic. So find the rate at which the volume of the balloon is increasing. So that's another way of saying find the rate in which the volume is changing over time interval. So, so in other words, folks, this is basically the formula. All we have to do is take the derivative on both sides of the variables, if you remember your derivative rules. If you don't, you're going to have to brush up on that. So that's going to be 4 pi r squared. Notice that this is going to be the surface area of the balloon times the tiny change of r per t. And there's the formula, folks. This is basically what they're asking. So find the rate at which this is changing when the radius is specifically 66.50 centimeters. Notice that it didn't take much effort to figure it out, but it also needs a variable when the rate is increasing at the rate of, that's another way of saying dr dt being 0.900 centimeters per second. So we know what the variable r is. We know what 0.9 is. So all we have to do is put 6.5 as the radius, 50 as the radius, 0.9 as the change of the variable. So that's going to be 4 pi times 6.5 square times 0.900. And I got that this volume is going to be 477.84 centimeter cubic, I think, per every second. And that's part A. Alright, that was pretty straightforward, folks. So let's do part B. If the volume of the flow rate into the balloon is constant, at what rate would the radius be increasing when the radius is 13 centimeters? The wording is a little off, but this implies that, it should say from part A. So if this is the constant change of the volume, so all we're going to do is, when the radius is 13 centimeters, we're just going to plug 13 centimeters in there and divide that. And you're going to have the change of dr dt being 0.225 centimeters per second. So that's what dr dt is. So, and part C is asking, explain physically why the answer to part A is larger or smaller. And realistically, I'm just going to put this formula all over again. 4 pi r squared dr dt. So think about this visually, folks. If this volume change is if the balloon is being filled with, is it air or whatever it is being a constant value, the larger this balloon is, the smaller the rate of the change of the radius is. And that's a formula you can just read off. and answer it in your own words if you want, or just look up the solution, or whatever you guys. Anyways, folks, enjoy.